Hello. Today I want to convince you that temDM MSA package is the best package for multivariate statistical analysis. You know, nowadays there are a lot of software for statistical treatment, but I will clearly demonstrate you that temDM MSA is superior. Well, speaking seriously, each software has its own advantages and disadvantages. What I'm going to do is just to highlight few very specific features of temDM MSA. Well, let's go to digital micrograph and we consider spectrum image. This is ill spectrum image. Let's pick some spectra. Yeah, and anticipating a little bit the complete treatment, I will show you the elemental maps. And from these elemental maps, you can appreciate that there is a strontium titanate substrate. On top of substrate, there is a iron selenide layer, which might be superconductive. And this layer is followed by iron telluride capping layer. Well, and our task is to treat this dataset with multivariate statistical analysis, mostly with principal component analysis, PCA. Let's open temDM tool for PCA, MSA PCA proceed. And first we have to prepare container. We choose the energy range, in this case the complete energy range, confirm. You might wonder why we need that container, but later on you will appreciate that it's very convenient. All the results of MSA treatment will be automatically stored in this container and you can anytime recover that. Well, then we need to proceed PCA decomposition. And I will use also some acceleration. It would be Python acceleration. By the way, the whole coming 2022 year, you can enjoy this acceleration free. Okay, Happy New Year. We extract maybe 10 principal components. Yeah, and after it will be finished, we see some preliminary results of PCA. This we can close. This we can close as well. Yeah, script plot is might be useful for us. Let's look at such presentation, and we can appreciate that about four principal components are meaningful. So we will use 4 components for reconstruction. Well, now let's reconstruct so-called denoised spectrum image. And here we are. Well, let's compare original and denoised spectrum images. We choose twin spectrum picker. Good. So we can travel along the sample, and you can appreciate that indeed spectra are denoised dramatically. Note this strontium peak. Well, that was denoising with temDM MSA package, and now let's try alternative software. That will be get an MSA plugin, which is included as default in the recent versions of GMS. Let's find it. Windows, floating Windows Technique Manager. I guess it is in data fit. Yes. It's not quite clear why it is in data fit category, because actually statistical treatment is not data fit, but doesn't matter. Here we are, MSA analysis, and we will click at simple denoise pattern. As in the previous case, it will decompose our dataset on principal components. And now the system will ask you how many components to use in reconstruction. We will choose 5 components in this case. One component more than it was with temDM MSA. Why there is such difference? We will discuss this point later. Right now, just choose 5 components for reconstruction. And here we are, denoised dataset. Let's compare the job of Getten and temDM. Click temDM, click Getten, and then choose Twin Spectrum Picker. Okay, we can travel along the sample, and you might appreciate that the denoising is quite similar. We can see quite nicely the shape of strontium peak. Yeah, maybe there are just very minor differences, but in general, it's quite comparable. So, our conclusion is, if we need PCA just for denoising, it doesn't matter which software to use. They all will generate the similar results, and also time consumed is similar. This is actually a common belief that PCA is nothing but a kind of denoising tool. However, to my very opinion, PCA is not just a denoising tool. PCA is more general. For denoising, we can use much simpler methods. For instance, Gaussian blurring can come to very similar results. Denoising is, of course, benefit of PCA, but not most important benefit. More importantly, with PCA, you can understand the internal structure of your data. What I mean, if we look more deeply into our PCA results, we will use View Result tool, and we can plot data distribution between first and second principal components. Here we are. Well, first principal axis, second principal axis, data distribution. And, well, we see some data trends. We can investigate that. Use Spectrum Picker. Spectrum Picker in that package is applied not only to spectrum images, but also to scatter plots. So please note, there is a certain green rectangular. We can choose with this rectangular data here, and we see the averaged spectrum. But what is more important, we see some kind of binary map. And with this map, we can see the correspondence between data in scatterplot and our normal coordinates. And very quickly, we discover that data distributed in that corner correspond to strontium titanate substrate. And if we move our selection rectangular to that corner, that would be iron selenide layer. And of course, the last corner corresponds to the capping layer. Okay, well, that was scatter plot using 2 principal components, but you remember there are much more. We can add the third axis and again plot the scatter plot. Well, in fact, there is also 4th dimension. We can try also to investigate the 1st dimension, scatter plot between components 3 and 4. But that would be not very informative because all data variations along the 4th axis are not so pronounced. So probably let's stay with three principal component axis, and already there we have quite clear idea how our data distribution is. Well, we are now in in space of 3 dimensions, and we can clearly visualize what's happening on in these 3 dimensions. I tried to make a simple plot of 3 dimensions, and what we see from these scatter plots in the plane formed by first and second component, our data variation is some kind of arc. And in the plane formed by second and third component, it's a kind of loop. And that's what I tried to sketch in this three-dimensional picture. Well, to my mind, that's very informative. We are now in new space, and in that space, we can very clearly say where are our compounds. This is ferrum tellur, this is ferrum selen, and this is strontium titanate. And what is interesting, it's not just some points or some spheres in that three-dimensional space, not some points corresponding to a certain compounds. There is always some variation, and this variation is not quite trivial. It's not something like straightforward variation between the given points in vector space. No, it's much more complicated. It's a trend, but quite interesting, with quite interesting form. Yeah, I suppose that is quite important finding. Always, I would say always, when we recast our data from one coordinates to another coordinates, we have a chance to make a new science. For instance, we see clearly the variation line in this multidimensional space. If we project all our data into this idealized line, we have a good chance to denoise our data much better than it was with standard PCA projection. I think introducing new carefully chosen coordinates is always beneficial for science. For instance, you know, when Laplace introduced new coordinates in mechanics several centuries ago, it was a kind of revolution. And also here, we have a new space. It might generate new idea in data treatment, but of course we are interested to make this space as compact as possible. At the end, we are 3D creatures, and we have problems in thinking in, I don't know, 5-dimensional space. Now let's come back to the question, why get an MSA plugin generated one principal component more than temDM plugin did? The reason for that is following. temDM counts data from the average spectrum, some kind of central point here and here. And that is the most elegant, most compact way of data representation in multidimensional space. It can be called centering of data, and this centering is the default option of extraction PCA components. Not like that in get and plug in. Get and plug in counts data from the 0 point where all energy channels are 0, and that adds an extra point in our multidimensional space, and according simple geometrical rules, it gives one extra dimension in our space. In fact, we can also disable centering in temDM MSA plugin. Let's do that. It's not recommended, but just for learning purpose. And we extract principal component again from the same container, but now without centering. The results are expected to be more or less the same what we had in the case of get and plug in. Let's check that. This is a script load. Let's look at that S line. And indeed, we can see that about 5 principal components must be retained, one PCA component more than in the case of centered treatment. Sorry. Well, now let's look loadings we probably do not need. Let's look at script load. Second component versus first one. It looks quite different from what we had in the previous case. And that is because now the scatter plot includes the 0 point, the point where all counts in all channels are 0, and that is somewhere here. Well, we can also retrieve the scatter plots with higher indices, for instance, third versus second, and here we are. You might notice that this resembles somehow this one. So probably we can conclude that everything is similar, but just indices of components are shifted to 1 inside towards the higher indices. And that is more or less roughly true, but if we try to extract scatter plot of higher dimensions, this scatter plot already would not resemble this one. Okay, as a conclusion, we can also operate within vector space in case of uncentered treatment, but the vector space would be more complicated and less convenient for navigation. Okay, I hope probably I convinced you to use this new space, vector space, and please believe me, it's a lot of fun to navigate in this new space. Yeah, I was able to design only a 2-dimensional viewer in this vector space, but now temDM MSA package is open source, so probably you can also design yourself some kind of 3D viewer, and that would be challenging. Also, I have to mention that there is another tool which probably is most suitable for navigation in the vector space. It is called temMember tool, but today we will not consider that. I think it's already time to stop, and I wish you all the best for today.